Welcome to my humble abode. And yes, kind of surprising that we're meeting here. I know there's this whole social distancing going on, but you gotta do what you gotta do. Math has to continue. Um, Due to recent developments, it has become harder and harder for me to get on campus. And so I am now actually working from home. Hashtag flatten the curve, hashtag stay home, hashtag math must go on. I will continue to record lectures, and this is not an April Fool's joke. It's the new normal, which I anticipate continuing until the end of the semester because I had some issues getting on campus yesterday, and I anticipate those issues continuing. So here we are. You will be joining me in my living room every day, and I will be sitting here because, of course, someone living in the 21st century needs to sit more often than they normally do, of course. So yeah, I saw a meme earlier today about essential workers and how they're kind of stuck between a rock and a hard place. Like on one hand, you're happy that you still have a job that you're getting paid for, but on the other hand, you'd rather be like everyone else working from home or whatever, but you have to actually still go to work. I feel like teachers have gotten the really short end of the stick because my life has gotten a lot more stressful since this whole stay-at-home thing has happened. I have to be prepping a lot more, and it's just overall very annoying, very stressful. My migraines are back to the daily now, whereas prior to this, I found my zen. I could go months without a migraine. Now I'm having them like on the daily for the past like week and a half. But we're here, and as far as I can tell, the only benefit to this new arrangement is that I can now go to work without wearing pants. And don't worry, I'm actually wearing pants. Yeah, which is very strange. I'm at home. It's a very rare occurrence for me to have those. But yeah, April Fools. All right, so that's the obligatory April Fool's joke. That being said, let's actually get into it. So I don't have a whiteboard, and no one's really ordering those, so I picked up one of these guys, which is what I'm going to be using to do math. And then probably I'll try to get a machete so I can get a haircut when this is all said and done. But that being said, we are going to continue. We're going to do the best we can. And that means OneNote, as far as I can tell. So let's me actually share that screen with you now. So welcome. This is Math 1203. We are continuing optimization. Let's get down to it. Let's not hold back anymore. So in my last lecture, I spoke about curve sketching, did another example, and then we started a new topic called optimization. Now, I did not get any questions on that lecture, which I assume means that everyone understood everything perfectly awesome, which is great. So we're going to continue. So for the rest of this lecture, I just want to do some more optimization problems, and just for you to get used to it, because we only did one example of optimization last time, going through those 6 steps, we're going to be doing that together now. So I'll be doing that on OneNote. I already copied the questions that I want to go over, but I will also be dropping a link to the PDF of the optimization handout in the description. But I copied a few examples that I want to do here. So examples 2, 4, and 5 from that handout. And another example, which, I mean, I numbered it here, example 8, but it wasn't numbered on the handout, it was on the last page. Without further ado, strange that you're in my living room, but let's get on with it. Yeah. Another thing I want to mention is that this, I will be able to get a PDF version of the notes here, which I will make available to you in a link again in the description. And I would recommend that even though I'm giving you the notes, that you should take your own notes, because the only thing that's worse than just watching me do all the problems and not trying them on your own is watching me do all the problems and not trying them on their own while not even taking notes, because that completely disengages you and it's just not great. So even though I'm going to provide the notes to you, I do want you to continue taking notes as if you were in the class. So you can pause the video if you want to take notes or anything, or even if you use my notes, make sure you copy stuff into your book and explain them in your own words, all that good stuff. So let's actually get into this. Let me move these examples out of the way, and we're going to start with example 2. So not much more conceptually, there's nothing new I'm going to teach. It's pretty much just us going through examples here just to get used to the process of doing optimization. So like I said, let's jump into more examples. Nothing really to talk about other than doing that. One thing I'm glad about is that this happened before, this happened after the curve sketching lectures, because I wouldn't want to have to do curve sketching on this thing. I've been trying to, still getting used to writing on this thing. It's very awkward for me. I hate a whiteboard, and now I'm on a digital whiteboard. It just keeps getting worse and worse. So yeah, even I've been trying this with a few lectures now. I posted some lectures where I did this, and yeah, even just me trying to box my answers was a horrible defeat. Hopefully I get better at this soon. Okay, enough is enough. Let's actually get on with it. I think I've been rambling for like, I should have paid attention to when I start. There's no timer on this thing. I'm guessing we're like 5 minutes in. I might be wrong. Okay, let's jump into it. So design an open rectangular box with square ends on the left and right side, having a volume of 36 cubic inches. That minimizes the amount of materials required for construction, because we want to save the earth, save the whales, all that good stuff. Let's actually get into how we would do this. So going back to our optimization, where are we? Okay. Going back to our optimization strategy, we know that step 1, why am I writing in red? Okay, let's fix that. Step 1 is to read the problem. So we know it's an optimization problem and all that good stuff, and we see the important stuff. Step 2 is to have a diagram. So you're going to try to conceptualize the problem. As a picture would be good. Here we know it's a rectangular box. Oh God, help me draw this. Okay. Boom, 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 bah, 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 bah. That was 1,000,000,000% better than I expected it to go, believe it or not. But with short strokes, it's like, okay, so they said the box was open. So that's open. Da, 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 da. In my other classes, we're going to eventually be drawing stuff in 3 dimensions, and I've always been proud of how I can draw things in 3 dimensions. But yeah, it's gonna be a really crappy show. Okay, so that is our diagram. That is a box. Now, can you properly label this box? Let's say you're labeling the dimensions X, Y, maybe Z, if you would need a Z, a third variable. So pause the video, try to label this correctly. Now, hopefully you pause the video and try to label it. Let me go on and label it for you. So let's say the left side is over here, the right side is over here. We're told that there are square ends. So if this length is X, that height must also be X, which means this width here, we weren't told about it. So I'll call that, don't know what happened there. So I'll call that Y. So X, X, Y, these are the dimensions. Okay, so the width and the height are X, the length is Y, and that is the diagram that was drawn and labeled. So we move down to step 3. Now remember, in step 3 of our optimization process, we wanted to find the constraint equation and the objective equation. Now remember the constraint. I was gonna just like, screw it, just leave it. But no, and this looks somewhat like a human being, Homo sapien wrote it. Okay, we have to come up with the constraint and objective equations. Now, I'm looking at the picture of myself. I should be looking over here. Okay, now the constraint is the equation that describes the restriction that you have. And remember the tip from last time. The restriction is going to be given by the thing that you're specifically told a value for. Now you'll notice here we're told that we have 36 cubic inches. Now cubic inches, that is telling you a volume. Okay, so pretty much our constraint here is that the volume is 36 cubic inches. And the volume based on my diagram is going to be x squared y, length times width times height, equals 36. And that is my constraint equation. Now, hopefully you got something similar when you tried this on your own. What would the objective be? Pause the video, try to come up with it. And I'm looking at myself again. See what you come up with. Now, hopefully you paused it and you tried it. Here's the objective. Surface area is our objective. That will minimize the amount of material used just by making sure that the surface area is minimized. So surface area is just the area of the 6 spaces. So I have the left and right side whose area is x squared, and that's just 2, and that's literally just where are we? That is for the left and right. This should not seeing where the thing is. Okay, so that is for the left and right. Plus, now the front and back is x and y. So 2xy is the area of the front and the back, plus now the base, x times y again. So this means that a equals 2x squared plus 3xy. And your equation should look something like that. You might have written x and y in opposite positions, that's fine, but you should get something like that. So here, just to make sure we know what's going on. Yeah, so this 2xy is measuring the front and back area. And this here is talking about the area of the base. So there are 5 sides to care about. The left and the right are 2, the front and the back are 2, and the base is the 5th face. It's an open box, so there is no top. So that is my objective equation. Now it kind of bothers me that that thing is in red. Hold on. One. Okay, now what was the next step? Do you remember? Pause the video and write down the next step. So hopefully you got that the next step was to find the new objective. Now the new objective, remember how we get that? You solve for one variable in the constraint and you plug it into the objective. So I would solve for y here. Now in general, it does not matter who you solve for, but it behooves you to solve for the person who's going to make your life easier. Now, if I were to solve for the x, I would get a square root here, which just makes your life harder. Why would you do that? Just divide by the x squared and you don't have a square root. Dividing by x squared it's easier than dividing by something and getting a radical in the denominator. So I decided to solve for the y, even though in general, I could solve for any one I wanted. I'm just checking that I am recording here because I don't want to have to go through all this and then turns out I wasn't recording. Okay, now where am I? Yeah, so this means that A, what I'm going to do now is I'm going to go to A, and everywhere I see Y, I am going to plug in 36 over x squared. Now, of course, I can simplify this a little bit. The square from this x is going to cancel that x over here. And so my new objective is a equals 2x squared plus 3 times 36, whatever that is, over x. So that's the new objective. This was the fourth step. What is the fifth step? Pause the video and say it. Or better yet, pause the video and do the fifth step. Which for this example, it's okay if you pull up the PDF to read over the steps, look at it, but eventually, of course, by the time a test comes around, whatever that's going to look like, you're going to want to be able to know what the steps are without having to look at the handout. Okay, yeah, and there I go, touching my face, bad Jhevon. Okay, so the next step is to actually find the absolute. Now, as I mentioned, the endpoints usually will not be the answer here, but you want to find the absolute max or min. Am I pressing too hard? I think that's not pressing too hard. I don't know why it's doing that. Okay, hold on. Yeah, I don't know what its problem is. Where are we? Okay, max or min. Right, now in this case, what we want is the minimum. Let's not do that. The minimum is what we want. That's horrible. It's a learning curve, people. Okay, so the minimum is what we want because we want to minimize the amount of material used, right? So in the says so in the question, we want to minimize the amount of materials used. Okay, so we want to find the absolute max or min of this. Now, of course, the extreme points are going to be like 0 would be an extreme point, and technically there's no upper bound here, but 0 obviously will not give you a box, so we can ignore that. We know that technically the local max or min is going to give us the actual maximum or minimum here. How do you find the minimum? Looking at the wrong thing again. Maybe I should put the picture of the video in the center. Ah, now you're thinking, Jhevon, even though that is kind of, yeah, that will probably block the thing for you guys. So let's not do that. Okay, so I'm just gonna, so if you see me looking off to the side, I really need to look at the camera directly. I'm looking towards where the picture is because I have a human brain. Easily distracted. Okay, so to find the absolute max or min, we're going to need to find the critical points. So we want to find A prime. That's going to give us 4x. How do I differentiate 3 times 36 over x? That's right. This would be 3 times. That's right. This would be 3 times 36 x to the minus 2, right? Because since 3 times 36 over x is 3 times 36 times x to the minus 1. So I could use the power rule, the constant stays, the negative 1 comes down, you subtract 1 from the power, so that is what you get. So in other words, this is 4x minus 3 times 36 over x squared. And you set that equal to 0 or undefined for critical points. Now, of course, it's undefined if x is 0, but that's useless to us, right? That's not gonna, x equals 0 is not going to be something that we want. That would mean there's no box. The length of the box is 0. It doesn't make any sense for us in this context. So we're going to want to solve that guy equals 0. So pause the video and actually work this out. If I were to set this equal to 0, what would x be? Pause the video, solve that equation. Okay, let's assume you solved that equation. If you didn't, pause the video, solve the equation. Don't let me do everything for you. This long distance learning thing, I mean, even when students are in class in person, they overestimate their abilities. It's going to be so much worse if you do the same kind of detached paying attention in a long distance setting while not taking notes, not doing anything. You're just setting yourself up for pain in the future, and I don't want you guys to have pain. So hopefully you did something like this. I would first clear the denominators by multiplying both sides by x squared. Then I would have 3 times 36 move to that side. Then this means that x cubed is equal to 3 times 36 all over 4. And 4 goes into 36 9 times, I would think. So that's 27, which means take the cube root, your x is 3. Now remember what I mentioned. Failure. Okay, now remember what I mentioned. When there's like one solution, you kind of know that's the solution that you want in this context. You kind of know that's the solution that you want in this context. Let's draw this circle very slowly. But you could test if not sure. And sure enough, if you drew a number line and you put a 3 here, you'd realize that you're decreasing over here, increasing over there, and you'd know that that's the minimum, that's the guy you want. So that completes step 5. We know that x equals 3 will give us the minimum dimensions. Which brings us to step 6, which is, that's right, answer the question. Now the question was to design a box. Now to design a box, you pretty much have to tell them the dimensions. Make the box this length by this length by that length. So to answer the question here, the dimensions would be good. So we want to be able to say length times width times height. Now we already know the width and the height. These are x's, right? And the length is the y. Now we just need to say specifically what values these are. So we know that y was actually 36 over x squared, which means here, this is 36 over 3 squared equals 4. So this means the dimensions is a 4 by 3 by 3 inch box. That's what you want. And we already know from the question that was about to be the best box I drew all day, but that last line just kind of messed it up. Yeah, I'm gonna leave that. So, because I don't think I can erase that like one little part, you see, I have to like like I have to like erase that whole line. Life is hard. Okay, so that's your answer to the question. That's the optimization problem. So to go back at a glance, optimization. You should know when you're seeing an optimization problem because it's going to ask you to maximize or minimize something. Here it asks you to minimize something. Read the problem. Draw a diagram that represents the situation. Come up with your constraint and objective equations. The constraint describes the restrictions that you have. In this case, the volume was your restriction. The objective describes what you want to maximize or minimize. You are going to solve for one variable in your constraint and plug it into your objective. Usually it doesn't matter who you solve for, but you solve for whoever makes your life easier. So because solving for the x would have created a square root, I decided to solve for the y. Plug that into the area, which is my objective. I want to minimize surface area. And then I want to find the absolute max or min. In this case, the min was what was required. So find the critical points, test all the critical points. Technically, we didn't have to test 0 because it didn't make sense for it to be 0. The only other critical point was x equals 3. So I know that that's the answer. If my x equals 3, my y equals 4, and therefore I know all the dimensions needed to design the box. So that is question number 1, which is technically question number 2 in the handout. And hopefully that was clear. If anything wasn't clear, of course, you can drop your questions down in the comment section or email me and we will go over it. But as you can see, we went through that 6-step process. And that's our answer. Let's do it again. So let's do example 4. Now I'm definitely going to run into these. So let's move these down more. Eyes are not loving me. They're suffering from digital eye strain today because, yeah, now I'm teaching completely online. Okay, let's move on to example 4 from the handout. So, of course, we are going to do step 1, read. And then we're going to set up a diagram, hopefully based on what we're reading. Hopefully that would give us some insight on what we want to do. A cylindrical can without a top is to be made to hold 8,000 cubic meters. Now, normally, remember I told you I don't really care. I'm looking at the picture again. Normally I told you, remember, I don't really care about units, but you need to kind of know about units to know, for example, when it's talking about an area versus a volume versus a length, this can be helpful. So here the 8,000 pi cubic meters is telling you a volume because it's cubic length units. Find the dimensions of the can, which will minimize the amount of material you needed to make the can. That is, minimize the surface area of the can because, of course, save the earth, save the whales. Hashtag stay home, hashtag flatten the curve. Okay, so here the diagram is just there's going to be a can. Is it easier drawing with a mouse? I don't know. This is all horrible. It's all horrible, whatever. Okay, so okay, so this guy is going to have a height. Let's call it H. He's going to have a radius. Let's call it R. And we're going to want to find the values of R and H that make sure the surface area of the can is minimized. Now, the important thing from here is to kind of figure out how you want to actually talk about the surface area of the can. Notice that the can Oh, here's another diagram. Okay. If I slice down one side of the can, right, and start to open the can, you'll realize it has, like, there's the bottom, which is a disc. And then if I slice vertically down at the can and open it up, it actually opens up into a rectangle. And then there is the bottom here. Okay, now this here we know is the height h, while this here is going to be what? What do you think it's going to be? That's right, the circumference. So it's 2 pi r. That's the distance around the top of the can. So here, basically, we would know what the area for that is. That's pi r squared. And here, we know what the area for that is. It's going to be length times width, 2 pi r h. That's going to be useful in the surface area later. So that's our diagram. We fully dissected the diagram. Did even a little expanded diagram right there, which is called, I forgot what that phrase is called, just slipped my mind. Is it schematic? It's not important. You know what I'm talking about. So now, yeah, that's our diagram. So that's step 2. Step 3, now you're going to talk about your constraint. And your objective. Now remember, the constraint describes your restriction. The restriction is the guy that you're given a specific value for. The can is, we're told, has a volume of 8,000 pi. Can't be whatever you want, has to be 8,000 pi. That's a restriction. So our volume is restricted here. In fact, it's 8,000 pi, which means our volume was the volume of the cylindrical can. Hopefully what you said is pi r squared times h. That is, it's a prism, so it's the area of the base times the length long of the axis. So that's our volume, 8,000 pi. Or in other words, if I have r squared times h, it gives me 8,000. So that's my constraint equation. What is the objective? To minimize surface area. What is the surface area? Well, we know it's comprised of these two areas put together. So it's just going to be 2 pi rh plus pi r squared. So that's our objective. Now, this brings us to step 4, which is to create the new objective. This means I solve for one variable in my constraint. Let's solve for h because it's the easier guy to solve for and for no other reason. Which means that if I plug that in, this is 2 pi r times 8,000 over r squared plus pi r squared. And you'll notice here that this r will cancel one of those squares. And so this can be, well, 16,000 pi over r plus pi r squared. That's our new objective. Of course, step 5. What is step 5? We all remember step 5. This is to find absolute max or min. And in this case, again, we want the minimum. So that's what we care about here. And we know how we want to find those. Basically, if you're finding absolute max or min, you're going to think about the closed interval method. So you're going to find out critical points. You're going to test critical points, test the endpoints. Of course, the endpoints here would be r equals 0 would be one extreme, which doesn't make any sense. So of course, again, we're going to have the local extrema being the solution here. So find the derivative, just minus 16,000 pi r to the minus 2 plus 2 pi r. And you set that equal to 0 or undefined for critical points. Now it's undefined when r equals 0, but it does not make sense for us to consider that situation because we would not have a can in that situation. So I'm going to ignore that situation and focus on where it is 0. So this means I have minus 16, 1, 2, 3 pi over r squared plus 2 pi r equals 0. Now pause the video and solve that equation for r, please. Okay, so now, hopefully, again, I would multiply both sides by r squared to clear the denominators. So that would be an r cubed here. This would mean that my r cubed is going to be 16,000 pi divided by 2 pi. That cancels that. 2 goes into that 8,000 times, which means your r is equal to the cube root of 8,000, which I believe is 20. So r equals 20. Now that's going to be our solution because it's the only one to speak of. Now, of course, you could test this and realize that it is actually a minimum. So now we are at step 6, which, as we all remember, is to answer the question. Answering the question would mean find the dimensions. This is r and h. Now r we actually already found. Now we know that h is equal to, I believe it was 8,000 over r squared. Yes, 8,000 over r squared. So h was equal to 8,000 over r squared, which is 8,000 over 20 squared, which is 8,000 over 400, I want to say. Cancel, 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 cancel. 4 into that goes 20 times. So h is also 20. So this means the dimensions, radius equals 20 meters, height equals 20 meters. This is going to not work out, but let's try anyway. Be brave. Let's box this answer. This is way harder than it looks. Oh God, give me a crick in my neck. Okay, so yeah, that's the answer for this one. Yeah, so again, same 6 steps: read, diagram, find constraint and objective, find your new objective by solving for one variable in constraint, plugging into your objective, find the max or min as appropriate, which involves finding the critical points, testing the endpoints and everything. Most of the time, your endpoints aren't going to make any sense. So you find whatever, you can test this number if you're not sure, and then you answer the question, give them whatever they ask for, the dimensions or whatever. And that is the problem. So hopefully you worked through that with me And that is the answer to problem 4 from the handout. Let's actually talk about problem 5. Now, especially if you haven't tried doing anything, you probably want to try doing problem 5. So there's problem 5. Scroll to problem 5 for your viewing pleasure. Can I actually? Want to make this bigger without messing up the margins. Let's just leave it. Okay, there's problem 5. Pause the video and try it. The manager of a department store wants to build a 600 square foot and rectangular enclosure in the store's parking lot to display some equipment. 3 sides of the enclosure will be built from redwood fencing at a cost of $14 per running foot. The 4th side will be built of cement blocks at $28 per running foot. Find the dimensions of the enclosure that will minimize the cost. Okay. Let me take a breather here. Yeah. Still have a headache. It's not super painful, but it's painful enough to be annoying. But let's keep going. Let's keep going. Let's do this for you, because yeah, we're all out here hustling. Okay, come on. I know you guys are working as hard as I am. Let's go. So 1, read. 2, diagram. Let's try to figure out what we're looking at here. We know it's a rectangle, which we know rectangles are hard for Jhevon to draw on this thing. I also know with this rectangle that one of these sides is not like the others. I don't know why it does that. Why does it do that? Right, so this is the side that is not like the others. Okay, so I'm highlighting the cement block side. All the other 3 sides are redwood fencing. Let's label this, shall we? So let's call this X. X would be that length. Y is this length. Y is that length. Now, we care about cost, so we should probably figure that out. So if we look at this side here, the cost of the redwood fencing is $14 per running foot. If this has X feet, this means that the cost here is 14X. Similarly, the cost here is 14Y. Similarly, the cost here 14y. The cost here, now this one is different. This is the cement block, that is 28 per running foot. So that's the cost there. That's our diagram. Moving on to step 3, we want to talk about constraints. And objectives. That's either ringing in my ears or my headphones are messing up. Okay, so constraints and objectives. Where are we? Okay, there we are. The constraint. The area is a constraint. It's 600 square feet, right? So I know it's a square foot enclosure. Square foot is a unit of area. So I know that the area of this is xy. X times y is 600. Objective is to minimize cost. My cost is just the sum of all the costs. So that's 14x plus 28x plus 14y plus 14y. So this means that cost is that 42? Another reason why I miss my students, so that they can do arithmetic for me. Like when you've been doing math for a long time, arithmetic just gets very annoying. It's like, oh, I have to do this again. Okay, it's very boring. Brain kind of shuts down. Okay, let's continue. So that's our constraint and objective equations. This brings us to step 4. Want to find the new objective. Next step in an optimization problem means I'm going to solve for one variable in constraint, plug it into the objective. I would probably solve for the y here because he has a smaller number multiplying him, but it's not really going to matter at the end of the day. Solve for the y, 600 over x. This means if I plug it into the cost function, I have 42x plus 28 times 600 over x. That's my new objective function. 5, we're going to find absolute maximum. In this case, again, we want to minimize the cost. And so what we're going to do is find the critical points here. So we're going to find C prime. It's going to be 42 minus 28 times 600 over x squared. Going to set that equal to 0 or undefined. That's not going to be something that we want, so now we're worried about this being 0. Now, of course, you know the usual deal here. Pause the video, solve this equation. Now, hopefully actually pause the video. I'm going to continue. I would multiply both sides by x squared. And so my x squared is going to be 28 times 600 divided by 42. Is that a nice number? It's too late, getting too old for this. That's 400, so that does work out nice. This is 400, which means that my x is 20. And so now Yeah, again, one X value, that's going to be the X value. If you're not sure, you can always do the test, do the first derivative test, and you can figure out that that will indeed give you a minimum. This leaves you with step 6. Answer the question. Now, what was the question? Find the dimensions of the enclosure that will minimize the cost. So we want dimensions. So y was 600 over x. Now y equals 600 over x. So that's going to be 600 over 20. That is going to be 30. This means dimensions. It's a 20 by 30 foot enclosure. Where cement blocks are on a 20-foot side, right? Because the cement blocks were running along the X, and the X was 20, as you would have recalled from the diagram up here, right? That situation will give us the best possible scenario, which is what optimization is all about, finding out the best situation given your constraints. That would give us the cheapest building of the cost of the cheapest enclosure. Now, I wasn't sure if I wanted to do this. That leaves us, that's the other answer. And again, you go through the same 6 steps. This is problem 5. Read, set up a diagram, find your constraint and objective equations. Constraint describes your restriction. Objective describes what you want to maximize or minimize. Find your new objective by solving for one variable in your constraint, plugging it into the objective. Find the absolute max and min of this new objective. Oftentimes the endpoints will not be the answer. Pretty much all the time in a Calc 1 class, the endpoints will not be the answer in a test. So you can often ignore that, and you find the critical points. And if you have several of them, or you're confused, is this actually a critical point? You can do a test to make sure that it's the critical point that you want. Answer the question after that. So you pretty much look for, what did the problem require me to do? And you make sure you do that. Give the people what they want. And that's that. Now, there is another application here of optimization for all you economics majors or people interested in economics, which I guess I'll go through quickly here because we're almost out of time, if not out of time already. Should have paid more attention to when we started. There's no like timer running on the screen that I can see. So my best guess is we're pretty much out of time in like a minute or so. Okay. Yeah, so inventory cost is the next application. So here's the situation. You own a store or whatever, and you're selling a certain amount of products, okay? So let's say you expect to sell a certain amount of products over a year's time. So, okay, I know for this product, I'm going to sell 10,000 of them over the year, but you don't have space to hold 10,000 units of this product. So what you do is you, of course, order in shipments. Like every month you might send in an order, or every 3 months or so on, depending on how much space you have, how many things you sell over whatever period of time. So the question is, what is the cheapest way to actually get all the items you need and are able to store it, right? So you want to actually minimize your inventory cost. So a useful equation in that regard is this equation here that you see, very useful equation. Now, what does that equation mean? Okay, so the total number of units, this is how much you expect to sell over a certain time period, say like a year, right? But you can't get all of these all at once. X in this equation represents the number of units you order each time for each shipment. So I might need, say, 12,000 over the year, but I decide to order on a monthly basis, and I would order 1,000 every month, so that at the end of the year, I would have ordered a total of 12,000 units. So in this case, my X is going to ultimately be 1,000, whereas the total number of units is 12,000. Now, of course, there will be costs associated with me ordering things like shipping costs, etc. So every time I make an order, there's going to be a cost associated with it. And so that's where this part of the cost comes from. The order cost times that guy. This here, total number of units divided by the units per shipment is how many shipments there are, right? So if I take 12,000 divided by 1,000, I get 12. That's the amount of orders I would make per year. Then I'm going to multiply that by the cost that it takes me for each order. Now, the inventory cost, this is measuring the cost it takes me to store the items. So whatever I'm paying for rent on the storage unit or whatever, right? How much it costs me to actually keep that inventory in stock is the inventory cost. Now, how we measure that is by the cost per unit. Now, for the per unit cost, we use X over 2. And here's the idea behind that. The idea is, if I look at the number of units stored, right? And this here is time over time. So let's say at time equals 0, I ordered X units. Then supposing I'm selling them at a constant rate, this is going to run out. There's going to come a point where I will have sold all those units and hit 0. Now at this point, or slightly before it, I'm going to order another X units, right? So this is, again, X units. And the same thing is going to happen. That's going to run out and hit 0. Then I'm going to have to order another X units, and that's going to run out, and so on and so forth, right? So I end up with the graph looking like this, right? So that's the graph of the inventory currently in storage, if I'm plotting it as a function. What you'll notice now is we just want to know, on average, how many products will I have in my storage unit at any given time? Well, it's going to be the average of all of these, which turns out, if it's at a constant linear rate, it's going to just be X over 2, right? That is going to be the average amount of products I'm holding at any given time. And this picture is actually on the last page of the handout, right? So on average, I have X over 2 items in my warehouse at any given time. So my inventory cost is per unit is going to be the inventory cost times the average number of units. This is the average cost of keeping these units. So that is this part of the equation here, where we have the inventory cost, and hopefully you can see that this part I'm looking at here, where you have the inventory cost times X over 2. That's where that X over 2 came from. So this is the cost equation for inventory. All right, it's a very simplistic model, but surprisingly very useful. And it's a model, it's an economics model, obviously. Okay, so that's the equation. So once you have an inventory problem, that's going to be an equation that's going to give you the inventory cost. Okay, that being said, let's move down to the actual question. What would a question like this look like? So here is an optimization that requires you knowing about inventory cost. Okay, so this is going back to Jevon's hot dog stand example, which I mentioned verbally a couple times, but I don't think I did it this semester too much. So Jevons sells 1,500 hot dogs per year at a steady rate. Okay, so per year, I know from my hot dog stand I sell 1,500 hot dogs. Okay, it costs him $2 to store each hot dog. So per hot dog, the space I would buy pay per hot dog is $2 per hot dog, right? As a storage cost, and it takes me $10 to order a new shipment of hot dogs. So that's the shipping charges for each shipment. How many times per year should Jhevon order shipments, and how many hot dogs would be in each shipment? So I want the number of orders I should make per year and how many hot dogs I should order for each order, right? So that's the question. So I know over the course of a year, I want to order 1,500 of them, but how many do I order each time? And hence, how many orders would I make over the year in such a way, of course, that I would want to minimize the cost of doing this, minimize the cost of ordering hot dogs and storing the hot dogs. Okay, so this basically comes down to you knowing this equation. We know that let X be the number of hot dogs in each shipment. Which of course would also mean that 1,500 divided by X equals number of times I should order, number of times to order per year, right? That's going to be the number of orders I make. Not per years, per year. Okay, so what does that mean? Okay, so if that's the X that I'm looking for, where's my point? If that's the X that I'm looking for, now we kind of skip the steps going straight into step 4. Because we kind of already went through the setup here. So technically it's new objective, quote unquote. Because the objective is to minimize costs. So I already have that in one variable. The constraints were individually dealt with, as I explained earlier, but I now know it's going to be order cost. Total number over X plus inventory costs, meaning the storage cost, times X over 2. And that's just from this formula here, which you would have memorized for this particular application. Let's create some space here. Okay, so what would our cost function be? Well, this would mean that my cost is the order cost. $10 to order a new shipment. So this is 10 times the total number, 1,500 over X, plus inventory costs. Cost me $2 per hot dog to store the hot dogs, times X over 2. So this cancels here. So pretty much what I have is C is equal to 15,000 over X plus X. So we now go to step 5. We want to find the minimum cost. So we're going to find the critical points. C prime equals minus 15,000 over X squared plus 1. Set this equal to 0 or undefined for critical points. Undefined, not going to do us any good because that would mean X equals 0. And yeah, I'm not going to order 0 hot dogs and end up expecting to get 1500 at the end of the year. So we really just want to solve this for 0. And of course, we know the deal here. Multiply both sides by x squared to clear the denominators. That shouldn't have been. So, boom. And this means that x squared equals 15,000. Is that a nice x? Did I do a typo here? Well, it does says 1500. Okay, let's see. 15, 1, 2, 3. If I took the square root of that, that's not really a nice number. I think I did there's probably a typo here. Anyway, whatever. Okay, so technically this is square root of 1500, 15,000. Now, more specifically, this is around 122.5. Okay, so I think in a test I'll give a nicer number here, something that will work out into an integer. I don't know why I have 1500. Did I mean 1600? Maybe I meant to type 1600 or something. Or 16,000, that would be a nice number, but who sells 16,000 hot dogs, right? Yeah, so this is about 122 hot dogs ordered per order. So this is this drawing boxes thing, which means number of orders is going to be 1500 divided by 122.5. All right, so that's a little over 12 orders. So pretty much once a month. Yeah, so let's make that approximately equal to, because I didn't pick nice numbers here. So pretty much once a month is the best time for me to actually order hot dogs. So whatever I want to sell in a year, under these conditions, if it costs me $10 to order a shipment and it costs me $2 per hot dog to store the hot dogs, I should be ordering hot dogs roughly once a month in order to minimize my inventory cost. And we're done. That took a lot longer than I expected to go through, but that's the last example. We are done with optimization. And by the way, that also marks the end of applications of derivatives. So we are going to be talking about a whole other thing starting next class. So hopefully you should look forward to that. We're going to look at the other thing that calculus was meant to solve, which I spoke about a long time ago. So pretty much this whole time we've been focusing on the rate problem, Come next class, we'll start focusing on the area problem, which I spoke about a while ago, and I will talk about again pretty soon. That being said, hopefully you understood this somewhat, the ideas behind it. If not, ask me questions about anything and try the problems on your own, the ones that I did not do, and let me know how it goes. Till then, it's late. I'm going to sign off. Hopefully that was somewhat helpful. I will put a link to these notes down in the description, but you should be making your own, pointing at the picture again. You should be making your own notes about everything here. Yeah, so that being said, stay safe, and I'll see you in the next one. Ciao.